So B7, we can prove in two different ways. We can prove it directly or we can prove it indirectly. So here what we're going to prove is if we have TS being the zero map, then when we want to prove that the image of S is a subset of the kernel of T, we can start by letting X be in the image S, then X equals S of V for some V in U. Then T of X equals T of S of V for some V in U. Then T of X equals TS of V for some V in U. Thus, T of X equals 0 as TS is the 0 operator. Thus, X is in the kernel of T. Therefore, the image S subset of the kernel T. So that's the way we could prove it directly. To prove it using the contrapositive, we assume that this is not true, that the image of S is not a subspace of the kernel of T. Then TS is not the 0. To prove this, let X be in the image S, but not in kernel of T. Then X equals S of U for some U in U. Then T of X equals T of S of U for some U in U as T of X, or as X is not in the kernel, as X is not in the kernel of T, T of X is not equal 0, thus TS of U is not equal 0. Therefore, there exists a U in U such that TS U does not equal 0. Therefore, TS is not the 0 transformation. So you can prove this in either direction. I naturally think of this direction, but many people actually found proving it directly to be a lot easier. So I wanted to show both work. Okay. Here, what we wanted you to do is we wanted you to describe in words. It was really testing, do you know the definition without relying on the symbols? So we have a function mapping one vector space to another. Such that the function distributes over addition and scalar multiplication. So it's very much in words what the function, what a linear transformation is. It's a function and what properties, with specific properties and what those properties are. So now what we're going to do is we're going to show that the function, there's a function that has one of those properties, but not the other. And what this is showing is it's showing that both of these conditions are needed. We can't just have one, we have to have both. So if you look at T Cx equals Ct of x, well, T C x1 y1 z1 equals root C x1 times C y1 times C z1, and it's cubed, which equals square root C cubed x1 y1 z1, which equals C root cubed root x1 y1 z1, which equals C t x1 y1 z1. So the first property is solved. But with the second property, if we let Tx equal 1, 1, 0, and y equals 0, 0, 1, then T of x plus y equals 1, whereas T of x plus T of y equals 0 plus 0, which equals 0. And I'll leave the details of that as an exercise. Now, finally, we have come up with an example of a linear transformation that is both injective and surjective, neither S nor T are injective and surjective, but the product of their composition is both injective and surjective. A classic example is T of x equals x0, or sorry, S of x is x0 and T of x y equals x. And now Ts of x equals T of S of x equals T of x0, which equals x. And this you can show is bijective. But this, because of the dimension, this is R1, this is R2, that tells us not surjective. And this here is R2 and this is R1, so T is not injective. So T and S are both not surjective and injective, but TS is bijective, satisfying the conditions that we have. If you were to put this on an exam, though, you would need to show that these are linear transformations. You would need to show that neither of them are injective. One is not injective, one is not surjective. And you need to show that the composition is a linear transformation that is both injective and surjective. Okay. And the extension question is an extension question. It's extending our knowledge. I'm going to leave that as an exercise. But if you have any questions, feel free to ask.